A forging can pass every dimensional check, meet every surface finish spec, and still fail in service. Not because the shape was wrong, but because the internal structure was never properly engineered. The parameter responsible for that structure is one of the most overlooked in forging procurement. It's called reduction ratio. Reduction ratio measures the degree of plastic deformation a material undergoes during forging. It's expressed as a simple ratio, initial cross-sectional area divided by final cross-sectional area. The higher the ratio, the more the metal has been worked. And that work is what transforms raw material into a structurally sound component. Higher reduction refines the grain size. It closes internal microvoids and shrinkage cavities, it reduces porosity, and it improves mechanical properties strength, toughness, fatigue resistance. But here's the critical point. This doesn't happen just because you apply more force. Reduction must be controlled and deliberate. Brute pressure is not the same as engineered deformation. When metal is plastically deformed under compressive force, its internal grain structure elongates and aligns along the direction of deformation. This alignment, often called fiber flow, is what gives forged components their structural advantage over castings and machined billets. In a casting, grain structure is random. In a machined billet, the grain gets cut through, but in a properly forged part, the grain follows the geometry. In a shaft, grain aligns longitudinally along the axis of rotation. In a ring, grain flows circumferentially, following the hoop stress path. In pressure-retaining components, grain orientation supports the stress distribution. This isn't accidental. It's engineered at the die design and preform stage before the first strike. How reduction is achieved depends on the forging process. In open die forging, higher cumulative reduction can typically be achieved for large cross sections, making it well suited for components where internal soundness is paramount. In closed die forging, deformation is more geometry controlled. The challenge is ensuring uniform structural refinement across complex shapes. Ring rolling introduces its own deformation pattern, radial and circumferential, which influences grain orientation differently from upsetting or drawing. The point is, process selection should align with the required structural outcome, not just the final part shape. In regulated industries, oil and gas, aerospace, defense, nuclear reduction ratio is not assumed, it is verified. Auditors routinely request documented reduction calculations, process sheets showing each deformation stage, validation of billet dimensions against final geometry, and inspection results confirming defect closure. Failure to demonstrate reduction planning doesn't just raise questions, it results in audit observations, non-conformance reports, and qualification delays. Because when a component is going into a subsea wellhead, a turbine rotor, or a reactor vessel, the question isn't whether it looks right. It's whether the internal structure can handle decades of service. Reduction ratio doesn't work in isolation. Heat treatment stabilizes and enhances the microstructure that deformation creates. But if the reduction was inadequate, even the correct heat treatment cycle cannot compensate for structural weaknesses that were never closed. And the chain doesn't end at heat treatment. Machining strategy matters too. Improper machining can cut through beneficial grain orientation, undoing what the forging process built. In an integrated forge-to-finish environment, machining allowances are planned to preserve fiber alignment, structural continuity, and surface integrity. Fragmented supply chains where forging, heat treatment, and machining happen at 3 different vendors often lack this coordination. At Vinir Engineering, reduction ratio is the starting point, not an afterthought. Every forging program includes documented reduction ratio validation before production begins. Grain flow planning matched to component geometry, not generic templates. A coordinated forging to machining strategy so that beneficial grain orientation is preserved through final dimensions. Integrated heat treatment monitoring and inspection-backed structural verification, including ultrasonic testing that confirms what the process was designed to achieve. We operate across oil and gas, aerospace, defense, nuclear, marine, and heavy industrial sectors. Each one demands deformation discipline that goes well beyond dimensional compliance. If your component's performance depends on fatigue resistance, pressure integrity, or long-term structural stability, the conversation needs to start with what's happening inside the metal. not just outside it. Connect with our engineering team. The link is in the description.